Morning everyone, and uh, welcome to this guest lecture by Professor Shinji Watanabe. Shinji, of course, some of you are familiar with Shinji, you're working with him. He is probably the best person on the planet right now to be if you're working on anything related to speech recognition and related topics. And we are lucky that he's actually going to be joining us in January 2020. Now, Shinji's specialty is end-to-end processing of everything. He calls it speech recognition, but he does signal processing, he does language modeling. The whole point is that he comes up with really nice ways of posing the problem such that you don't have to worry about the innards of the problem. You just provide these networks inputs and outputs, and they learn how to do everything. So I'll hand this over to Shinji. And Shinji, the floor is yours. If there are, I'll be manning chat, watching questions. Rashmi and Kushal are here. They too will be tracking the chat box for questions. So if there are any questions, we'll forward them on to you. And of course, students, you guys are always welcome to ask questions anytime. Shinji, the floor is yours.
Okay, thank you, Big Share. And today I will talk about the bit based on my the personal experience. But I think Big Share already they explained about the CTC, attention-based encoder decoder, and so on. And my kind of lecture is somehow they try to kind of compensate how we kind of apply such problem to the more realistic application. In my case, is speech recognition or some other speech the processing applications, and that would kind of have a good compensation of the theory and practice, I believe. So let me explain about this presentation, how I organize it. Again, this is based on my personal experience. So some other people may have a different way of the organization of this kind of a talk. But I would say I am one of the early adapter of the end-to-end neural network for speech processing. So with this kind of experience, I can tell you what was the kind of difficulty, what was the kind of the extension we came up with. Such kind of personal research experience sometimes is quite, how to say, informative for the students. So I picked up this topic rather than having a more kind of detailed normal style lectures. I can also do that, but this time I picked up this a little bit kind of the official way. Yeah, when I was a student, I actually enjoy such kind of the professors' personal research experience in addition to their great lectures. So actually, it turns out I remembered most of the lectures with their the real world, their real kind of personal experience about the research. So that's why I also picking up this topic. And I am assuming people have some end-to-end neural network knowledge. And I think that should be right because, again, I checked the syllabus and the previous lectures focusing on CTC and attention-based encoder decoder and so on. Okay, so again, I reorganized my kind of several talk with the chronological order. So someone that joined some of my talk may know a little bit about this topic, but please enjoy this, how to say, historically, how I kind of think about developing such kind of end-to-end neural network. And this is a kind of a timeline. So the first, I started this topic in the 2015. And it's actually 2015. It's more like I still in the learning status. And 2016, I started to implement a lot of end-to-end speech processing techniques by myself or with the help from my colleagues. And then given this the experience, I moved to the Johns Hopkins, and they started the open source activities. And 2018, the mainly I was working on the speech recognition, but it turns out that sequence to sequence end-to-end neural network is quite general to be applied to various the speech applications. So I am also working on this area, and since the everything is now written by neural network, as soon as we get some good neural architecture, we can easily incorporate such kind of problem to the existing end-to-end neural network. So I will explain about how we kind of improve the performance with this kind of the architecture. So again, this is more like my the timeline, the history of how I develop end-to-end neural network. Okay, let's first discuss about the impression part. That part was again before I started to implement end-to-end neural the model to speech processing. And before that, I would like to briefly discuss about what is speech recognition, which is formulated by noisy channel model in 1970 or maybe the earlier than 1970s, depending on the definition of when we started. But this noisy channel model is a quite powerful problem at that time to make a relationship between the sequence, input sequence, and output sequence. In the speech recognition cases, input is the sound, audio, the signal, which is a physical signal sequence. And actually the time domain, the pressure of the sound was regarded as the speech, the signals, so that usually we have the very long sequence. It depends on the sampling rate, but let's say we usually using 16,000 the sampling rate and the speech recognition, and then the length of the signal of the one sentence can be easily the order of the 10,000. Like one example of this audio signal, only 3 the second of the signal correspond to the 43,000 of the very long signal. But it is one-dimensional. And the people using the more like a spectral the representation, short-term Fourier transform to change the signal representation to a little bit shorter one, like 268 is a general the conversion from the time domain signal to the STFT signal. Such kind of very long sequence was converted to only the 3 lengths of the word. And this the word is linguistic symbol. It doesn't have a physical signal property anymore. And the speech recognition is a kind of a such problem. Input is very long physical signal. Output is a linguistic symbol, and that property is very, very different. Okay, how we try to solve this problem? First, we use a Bayes decision theory. We first make a probabilistic distribution, PW given X. Here, W is a text sequence and X is a speech sequence. Once we get this the probability, we can perform the speech recognition by picking up the most the highest probability word sequence, and regarding it as the recognized the text. By using this, we can mathematically formulate this sequence-to-sequence mapping problem by using the Bayes decision theorem. However, this the how to obtain this probability distribution was not easy in the 1970 eras. And actually, what we try to make this problem tractable is using the probabilistic rules. For example, we first use a Bayes rule to decompose the probabilistic distribution to these two distributions. And this is not enough. At that time, we also include the intermediate representation of the word and the speech, which is phoneme. And by using the phoneme, we can further factorize this probabilistic distribution. By the way, there are a lot of, from here to here, we have a lot of approximation. Like here, we have a conditional independence assumption. We also actually need to have to marginalize the phoneme sequence intermediate representation through the summation over all possible phoneme sequence here, sum rule. But instead, we just using the maximum L to approximate the problem. So from here to here, this is equivalent. From here to here, we actually put a lot of the approximation. And one of the important approximation is a conditional independence assumption applied here. And the conditional independence assumption is not only applied here. Actually, even we decompose this original probabilistic distribution to three distribution, it is still not tractable. For example, Px given L is called acoustic model, which is converting the phoneme sequence to the speech sequence, but it is still not tractable at that time. And what we try to solve it, we use a hidden Markov model, Markov assumption. It's a kind of one instance of the conditional independence assumption. And we also have to have a lexicon and the language model. Language model, we also at that time using the n-gram, which is based on the conditional independence assumption. So let me summarize this methodology. To solve this very difficult distribution, how we solve this problem? We first factorize into several components, and we set the conditional independence assumptions, and then make all the kind of a probabilistic distribution tractable, and estimating each of the distribution from the training data, and finally perform the speech recognition. By the way, this is not applied to the only speech recognition. This noisy channel model can be applied to various problems. One of another successful application is machine translation. Here, W becomes the target, the word sequence like a French, and X would be the source, the text sequence like English. And basically same. We factorize the probabilities, put the conditional independence assumption, and then making it tractable. And this methodology was very good. With that, we can realize this kind of very complicated problem realized by our computer. And this methodology actually continued over 40 years. However, this methodology also introduced a big problem, big barriers. Again, the HMM n-gram noisy channel model, this actually apply a conditional independence assumption. Is conditional independence assumption true? Sometimes not. We actually have to consider very long context. But HMM n-gram and other models are making it tractable to this problem. We actually aggressively remove this dependency. So before, actually this was the big barrier, And a lot of researchers try to overcome this problem by extending HMM or by extending n-gram and so on. However, this big barrier was broken by sequence-to-sequence based neural network. So in this the lecture, I will mainly talk about end-to-end processing using sequence-to-sequence neural network. As you know, it's not decompose each the model anymore, but the model directly try to estimate the probabilistic distribution PW given X with a single neural network. By the way, it also turns out that internally, each of the neural network, part of the neural network correspond to the acoustic lexical language model. We can actually making such kind of interpretation as well. And then this single neural network does not only mean that it is a just single black box neural network. It actually have an ability to integrate a lot of components to finally make it as a single neural network. And again, this the method is not only for the speech processing, actually has a great success already in neural machine translation. And this lecture, first I will briefly introduce this sequence-to-sequence problem with the two the realization. One is CTC. Again, that I basically don't briefly explain this CTC since it was covered in the previous lectures. But I just want to mention that the CTC is the first instance of the speech recognition based on end-to-end, which directly predict the speech features to the token, the text sequence. However, to adjust the mismatch of between the input and the output sequences, CTC is using dynamic programming based on the conditional independence assumption. Second one is attention-based encoder-decoder. Again, I didn't fully explain about the detail which was covered by the previous lectures, but I can give you several kind of different view of the attention-based encoder-decoder. As you know, the attention-based encoder-decoder, which is composed of encoder, attention part, and decoder. And this part seems like very different from the original the acoustic model, language model in speech recognition. However, we can actually interpret encoder part as an acoustic model in speech recognition. Attention decoder part can be regarded as an HMM or lexical model, and the decoder network part is exactly similar to the language model, except that its hazard context vector comes from the encoder. So attention-based encoder-decoder can be viewed as a single neural network to include all acoustic HMM and language model in a single architecture. And now I move to the my kind of the experience about first I the the started to study about attention-based encoder-decoder. I was actually very impressed by this approach because it doesn't use any conditional independence assumption, which was the most important part of making the speech recognition tractable in HMM. And actually CTC is also regarded as an end-to-end speech recognition, but using conditional independence assumption load everywhere. However, attention-based encoder-decoder basically the solving PW given X with this probabilistic chain rule. That's it. And the probabilistic chain rule has never had any conditional independence assumption. So that is the more precise sequence-to-sequence model, I would say, in terms of the conditional independence assumption perspectives. And again, not only me, but many of speech researchers or machine translation researchers have been struggling conditional independence assumption. And this is the one first solution I saw that we can actually escape from the conditional independence assumption. So I was very excited about this method. And then I started to the work on this attention-based encoder-decoder in 2015. However, I encountered one very difficult problem, which is attention mechanism. That is great in terms of the connecting the input sequence and the output sequence in the neural network manner. However, it turns out that it is too flexible to train it. So now I move to the my the experience of the initial implementation of the attention based encoder decoder. So given the several kind of studies, we started to implement attention-based encoder decoder by ourselves. And it was I would say the compared with other big speech project in the giant like Google and Amazon and so on. This project was a quite small project, I would say. And actually, the one of the main person was the Soo-yeon Kim. She is now in the Facebook, but used to be she's the student, PhD student in CMU. And this project was started when she joined the MARO, Mitsubishi Electric Research Laboratory, during summer internship. And me and Takaaki Hori in the MARO, and sometimes John Hersey, these four people are mainly working on this project. And first, we implement both CTC and attention-based encoder-decoder by ourselves. Of course, we use several libraries, but we basically implement them by ourselves. Not that at that time we didn't have a PyTorch. We have I think TensorFlow was already there, but it was very early stage. And we use several other the neural network toolkit like Cyano and so on. But it was a little bit difficult to implement the flexible attention-based encoder decoder. So we at that time we picked up the toolkit called Chainer. I don't know how many people know this the toolkit Chainer because now the Chainer's the main the development was stopped. But Chainer was the one of the first dynamic neural network toolkit. And later, the PyTorch actually started to be developed based on the very initial version was the fork of the Chainer. So Python, the Chainer is a kind of a, how to say, the brother or sister of the PyTorch. But China was the developed the very early stage, 2015. They are already matured already. Anyway, with this the implementation, we found several pros and cons. First, CTC. CTC not only based on the implementation, but we also studied a lot more about what is CTC. And yeah, I think now it's obvious, but what we have encountered is that CTC has a lot of conditional independence assumption. Actually, the degree of applying the conditional independence assumption is quite similar to HMM. And the one of the important part of the CTC is that there is no explicit modeling of the output label. So it's the good model, but it doesn't include the language model types of the effect in the model itself. So we found that that was a big limitation because language model is quite powerful in the speech and the other sequence generation the problems. Next, attention-based encoder decoder. Again, this doesn't have any conditional independence assumption. And we are very excited about this the neural network architecture. However, attention-based mechanism was too flexible to get the alignment. And we have a problem to train the model from scratch. So I will explain a little bit more about the alignment assignment issues. So HMM, CTC, both are based on the state transition problem. So that if we, for example, the generate the one kind of character or token given the input. Next, the state. When we move to the next state, it actually has to be predicted by the next chunk of the frames. State transition model explicitly set this kind of alignment property. And this alignment property is called monotonic alignment. So this is the figure of the alignment process. This is the input, and this is the output, and this line correspond to the higher probability of the input aligned to the output. And as you can see that it is a kind of a one single line. And there is no, how to say, no other the line or no other blurred the pictures, just a one line. This shows the monotonic alignment. Is there the other cases? Actually, the attention-based model doesn't assume this kind of monotonic alignment, which is good for the machine translation because machine translation, the order of the input and the output relationship can be different. So this kind of a flexible alignment should be allowed in the machine translation. However, the speech recognition, it must be monotonic. And then what I encountered, the problem is that the alignment is not well obtained. It's always like a broken, like this. This kind of alignment should not be appeared in the speech recognition. However, attention-based encoder-decoder is too flexible. And this kind of solution is actually possibly obtained. And we encountered the problem of how to get a very clean picture of the alignment. So then we try to came up with the solution of getting the better alignment. So how to solve this problem? Yeah, we spend a lot of time actually try to solve this alignment problem by, for example, explicitly forcing mathematical representation of the monotonic constraint in the encoder decoder and so on. We actually had a lot of trials, but any of the ideas actually losing the benefit of the attention-based encoder decoder and actually degrade the performance. And we cannot well come up with a good approach of using the both benefit of the CTC, which has a clear monotonic alignment and attention. And there are several other approaches to overcome this problem. One possibility is RNN transducer. This is an extension of the CTC by considering the language model component in the CTC, I would say. People can say a different way of RNN transducer. But this would be a one solution. And then we finally came up with the idea, which is simply combining CTC and attention in the multitask manner. And that is actually, we initially came up with this idea, but we didn't try that because it is too straightforward. And we also didn't kind of we are not convinced that this kind of a simple the combination would work. But it actually turns out that working quite well. That is our very beginning of the CTC attention, the hybrid or joint network. This approach is quite simple. Instead of having an attention-based encoder-decoder, we just combine CTC loss function as well here, so that this CTC branch can implicitly force encoder to make a monotonic alignment. And it was actually working well. CTC guides attention alignment to be monotonic implicitly. And we actually have very nice pictures about the how the attention was corrupted and it was recovered by using the simple combination. The first the line of the figures are attention-based model. And of course, sometimes most of the cases it's working well, but some cases attention is corrupted. We cannot get the clear attention picture. But our previous multitask learning can uh, implicitly forcing the monotonic alignment. And in very early epoch of the training, we can easily get the monotonic the alignment. So that was our kind of the first solution of obtaining a monotonic attention in the encoder-decoder, attention-based encoder-decoder architecture. However, this approach is implicit. This CTC, the objective is only forcing the encoder, and there is no explicit control of the attention, the network. So we actually cannot fully eliminate the alignment issues. And later, we also come up with another idea. Since CTC and attention-based encoder-decoder are solving the same problem, both can produce the text information. So our idea is during the beam search, we actually combine these two outputs. And at least CTC having an explicit the monotonic alignment property. So by combining two results, and if we kind of eliminate the irregular the alignment comes from the attention-based the encoder-decoder during this combination, we can completely ignore the alignment, the wrong alignment problem in attention-based encoder-decoder. So these are the combination significantly improve the performance by eliminating the irregular alignment. So this is the two benchmark of the speech recognition. The one is the Mandarin Chinese telephone conversation task, and the other is the corpus of spontaneous Japanese. And this is the error rate. So lower is better. And the first attention-based the model get some the reasonable performance, but we check the kind of the attention pattern, and it turns out a lot of errors comes from the wrong the attention patterns. So the first idea of using CTT as a multitask learning improve the performance. and the combination during the inference further improve the performance. Same effect is observed in the another task and so on. Multitask improve the performance, and the joint the inference improve the performance further. And I will explain about some other example. And this is a very typical example of attention pattern, attention mechanism was failed. And this actually example is not only happened in speech recognition, it's also happened in machine translation often. So in this figure, there is a three kind of attention patterns are looped, right? And this is actually clearly wrong attention pattern. And what's happened in the speech recognition result? You could see that these phrases are repeated 3 times. So these three lines of the attention correspond to the generating the two same phrase, two wrong the phrase in this attention pattern. So again, this is a very typical errors of the attention-based encoder decoder. If we have a better model, we can eliminate this kind of problem to some extent, but we always observe this kind of errors. However, by using the combination of the CTC, we can have the monotonic alignment property, and we can actually solve this the weird attention patterns. Another example, this is also very famous, the example of the attention is failed. You could see that attention weight was stopped in some input, and there is no output. And this corresponds to the recognition result of this wrong pattern. Basically, for the beginning part, it produced some result, speech recognition result. But later, this completely stopped to output speech recognition result. And then that's the and then that's the pattern can be recovered by using the joint modeling and so on. And I have a question from the in the chat window. Monotonic means the order synchronous. Yes, exactly. We can also call it as a synchronization. Synchronization of the input and the output with data without changing the order. So this the sync yeah, we can also rephrase it as the synchronization, but this one in terms of the alignment the context, we call it monotonic alignment. Anyway, by using this problem, by using these techniques, we can somehow avoid the problem happened in the attention-based encoder decoder. And now the discussion. With a lot of kind of the effort of the implementation of the CTC and attention-based encoder decoder, we actually found the pros and cons of the each approach. CTC is the good in terms of getting a monotonic alignment, but it doesn't have the language model types of the effect. Attention-based encoder decoder, basically the vice versa. So by combining CTC and attention-based encoder decoder, we can completely solve the end-to-end the speech recognition alignment issues. And given this successful the application, now I actually started to apply this end-to-end neural network to various problems. Once attention-based encoder decoder came to the community, we are actually again very excited. And I had a lot of ideas of using this kind of architecture, but it turns out that the alignment problem is quite difficult, and we cannot safely extend attention-based encoder decoder. But with this hybrid approach, we can now have a safe way to get to the alignment, and we can move to extend end-to-end neural network. That is again my kind of research history. First, we solve the attention-based, the monotonic attention problem, and then apply to the other problems. And there is a one note. This attention-based problem, attention alignment problem, can be solved by large amount of training data or a lot of tuning. This is one solution. So actually, people in Google or people in the other big companies which can have a good access of the large amount of training data and have a good computer resource of the lot of tuning, they actually would not encounter this problem, or they could encounter this problem, but they can solve this problem by using the high computational resources. However, in this approach, I would say it's a kind of academic friendly approach. Even we don't have a large amount of training data, even we don't have a lot of kind of the computer resource to tune the model, we can get a solution. So this the approach is not the widely used in the industry level. But this approach is actually quite frequently used in the research phase, so that we don't have to care about a very large amount of training data or a lot of tuning. And I also want to have the kind of a FAQ. I got a lot of questions about how to debug attention-based encoder decoder. And many people are just, yeah, it is not easy because it's a single neural network. And one of the kind of criticism of the neural network is it is black box, right? However, there are some hints for us to debug neural network. One is attention pattern. Attention-based encoder decoder, you should definitely check attention pattern. And learning curve as well, which is more like a general machine learning the problem. But the learning curve, you should definitely check always. But in addition to do that, attention-based encoder decoder, you should always check attention pattern. And then you can figure out what happened inside. So that is my recommendation to debug this very complicated single neural network. This is one thing I actually like attention-based encoder decoder, because attention is more intuitive than just having hidden state vectors. LSTM is, for example, very cool. It has a cell mechanism, and people can interpret this cell mechanism to have a long memory. But actually, inside cell and gating is continuous vector. So it's not actually easy for us to interpret what happened. Attention is quite easily interpret what happened. So I strongly recommend you to the maker the attention, check the attention. Yeah, and this the picture also mentioned that pay attention to the some of the homework, I guess, is the implementing attention-based encoder decoder. Yeah, before asking TAs or picture, you should carefully check the learning curve and attention pattern. This gives you a lot of hint. Okay. So given this, given this the experience, what I started to do is actually extend this idea to the other the application. And here I actually have a lot of applications for the attention-based encoder decoder. But here we also introduced the multilingual speech recognition as a one the very strong application of the end-to-end speech recognition. So let me going back to the original speech recognition method, which has several modules: feature extraction, acoustic modeling, lexicon, and language modeling. And again, this is based on the noisy channel model. A lot of conditional independence assumption, making each problem tractable and realizing the speech recognition before end-to-end neural network error. And I would say that this methodology is also very powerful and strong. However, this, I would say it's not a drawback, but it's a more like a characteristics compared with the end-to-end neural network. Instead of the end-to-end neural network-based approaches, this modular-based approach require a lot of development, I would say. We need to implement feature extraction. We need to implement acoustic model, lexicon, language model. Each of them are different model. So we actually cannot use a single, for example, neural network toolbox to implement this one. Here we need to use some signal processing toolbox. Here we have to use some other, yeah, it's more like a pattern recognition, GMM, HMM, or deep neural network combination. But you need actually such kind of extra implementation. Lexicon basically kind of a database. So we need to have a kind of implement the model to access the database and to get to the pronunciation lexicon. And the language model, which is again another kind of the modeling, and that is different from the other modules as well. And again, this is great in terms we can kind of separate, modularize the problem to each of the component so that we can easily implement each of them. But it turns out that implementing all four components and maintain it is actually big pain. And for multilingual speech recognition, there is actually one of the most difficulty part is the lexicon part. We actually have to prepare the word list and the corresponding pronunciation dictionary. By the way, I extracted this one from the CMU dictionary, which is another great contribution of the CMU to the community. CMU is the maintain such kind of the very large scale English pronunciation lexicon database so that everyone can easily perform the speech recognition in English. Other language are different story. And this is another reason that English was often used for the speech research because we have CMU dictionary. So be proud of being a CMU student. Okay. However, this maintaining this kind of lexicon is very difficult. And of course, if we extend it to the multilingual, we need to maintain this kind of dictionary for each language, Japanese or Mandarin or Hindi or German or whatever. So if try to have a multilingual 10 language, we basically have to have a 10 the dictionary. So this is actually one of the big pain. So this is the kind of a big reason. A lot of development and maintaining the linguistic resources is not easy for the small resource, the research institute to do. So that's why the building speech recognition systems, especially in the multilingual context, is not that easy. And only the big companies can build a speech recognition system by themselves, or only big research institute, including CMU and Johns Hopkins, can build ASR systems, but the other universities cannot, something like that. So end-to-end neural network is the changing this story. Again, instead of having a whole independent module, it can be implemented by single neural network. And it's actually does not require lexicon, pronunciation lexicon. So this means that we can exclude the such kind of linguistic information here to get the neural network. By the way, I just want to note that this is the pros and cons. Sometimes it is very good to use the linguistic resources, including pronunciation lexicon. However, end-to-end neural network actually is not easy to use this kind of a great resources due to the single black box neural network architecture. Here, I use this kind of a part as an advantage, but it can be disadvantage. Also, the other possibility of the single neural network architecture is that we can also get the global optimization of the single neural network rather than separately optimize each of the module. So this is the benefit of the end-to-end SR. And again, once I implemented hybrid the CTC and the attention the method, and in the English, mainly in the English database. And then the next my action is to apply to the other languages. And what I first tried was Japanese. Uh, Japanese is actually one of the very difficult language to build speech recognition system without the linguistic resources. So this is the typical example of the speech, text in Japanese. First, you can find that there is no word boundary. And the second, it's actually including the full script. That is very casual in Japanese. And I think the other, how to say, the language that also have this kind of problem. In Japanese, we have to handle 4 types of the script. Hiragana, katakana, kanji, and the Roman alphabet is also getting popular. And this kind of sentences very often they happen. And the other difficult part is that this, if we get the pronunciation from this sentence, it's actually many to many pronunciation. Japanese, it has a lot of homonyms and a lot of multiple pronunciation for each other. So this is another thing that we need a very, very kind of a good dictionary. By the way, in Japanese, we don't have we have a CMA dictionary equivalent one, but it's actually the dictionary, pronunciation dictionary is changing depending on the context. So we don't have a one-to-one mapping. We basically have to consider sequential processing, context processing, and then getting the phoneme, the approach. So Japanese, the pronunciation, the lexicon was actually very in the beginning stage. We used the HMM or CRF or other sequential the processing toolkit. Otherwise, we cannot actually get a good pronunciation lexicon. And also, there are a lot of mixed the script again. So one of the character may correspond to very different duration. This character only one phoneme. This character, this actually correspond to the samurai. Some of you may know soldier in Japan. It is actually having how many? 1, 2, 3, 4, 5, 6, 7. Yeah, 7 phonemes and or 4 syllables. And one of the characters' duration is very different. It can be the order of the 10 second or 100 second. It can be an order of the 100 to the 1 second. So one of the character may correspond to a duration of the one of the character is very different. And again, to deal with this the language, we have to have a very accurate tokenizer, and the tokenizer is actually performing the morphological analyzer and the pronunciation lexicon at the same time. this kind of a tokenizer was super important in Japanese. And we actually need to have a great help from the linguist or natural language processing researchers. There is a very famous lab, the Nice Nara Institute of the Advanced Institute of Technology, and this Matsumoto lab is the one of the kind of leading the NLP research the groups in Japan and in the world, and they actually the maintain this kind of tokenizer. Otherwise, we cannot use the speech recognition, Japanese speech recognition. However, what I did was I directly feeding input audio and this mixed character list and making a single neural network to predict it based on attention-based encoder decoder. We don't use any tokenizer, we don't use any pronunciation lexicon, which was the people thought that it was impossible for Japanese. But it turns out that the performance was actually very good. The initial the trial of this approach is the character error rate is around 10%. Error rate, so lower is better. And now actually our approach is in the same task 5% or 4% of the ball as a ball task, a ballpark. And again, this doesn't require any linguistic the resources to only require the pair data to realize the speech recognition. And this is one of my dreams, but it was easily realized by attention-based encoder decoder. So I was very kind of excited about this result. And this result further convinced me one direction. As I said, Japanese ASR, which is mixing four script in the one language, so that maybe single neural network can deal with multilingual multiple languages, including English and the other languages and so on, or even we can perform the code switching. So this is another application of the multilingual speech the recognition application. Got a hint from my experience of applying attention-based encoder decoder to Japanese. And what would be the kind of the extension? This is a conventional speech recognition, as I mentioned, the speech recognition pipeline for the single language. And the multilingual speech recognition, what we usually implement is we first have a language detector and the corresponding speech recognition for each language has to be built. But given my the experience of the Japanese speech recognition, I saw that we can mix everything and realize it with a single neural network. That is kind of the second application I came up with this the single neural network architecture. By the way, as a demonstration, I also have several other crazy ideas. For example, why not we also consider multiple speakers speaking at the same time, and then recognizing this speech. Here, we need to have a speech separation module and separate each of the speech stream. By the way, this speech separation, Big Shah, Professor Raj is the one of the pioneer of this speech separation, solving the speech separation problems. And we are actually basically having this, if we try to kind of solve multiple speaker problem, we actually have this kind of speech separation component. And if these are different language, we may have to prepare different language of the ASR system. But that can also be performed by a single neural network. That is also we actually tried. Again, once attention-based encoder-decoder started to work, we have tons of ideas of solving this kind of problem. And I will a little bit kind of dig in the how we solve the multilingual end-to-end speech recognition. And this was actually in this work, I kind of targeting to 10 languages. And if without the end-to-end the modeling, again, developing the 10 language speech recognition system is not easy. We need to have a lot of resources to build this kind of system. But I try to kind of integrate all the 10 language as a single neural network. How to do it? I actually mix all languages, the English, Japanese, the Mandarin, the Russian, and so on. So it's just kind of expand the vocabulary to the English and the Japanese and so on. And we prepare the English sentence and the pair, English sentence and the audio pair, Japanese sentence and the audio pair. That's it. We just kind of prepare the data, parallel data, and mixing all the language. And why this can be working? This is because we don't have to prepare the pronunciation lexicon. So this is the first trial of the multilingual speech recognition. The red blue bar is more like a conventional system. We build the speech recognition system for each language. And the red one is just having a single neural network to accept 10 languages and having a recognition. So this one, by the way, this means this the neural network internally also have a language identification, the functions. And by using this single neural network, we could have actually some of the high resource language, the performance is slightly degraded, but some low resource languages actually having a very large improvement. Mainly comes from the sharing the data, so that we can actually avoid the overtraining in some of the encoder layer, which is more like a language independent part. Decoder network can be a language depot. It's implicit, but can be a language dependent. So the effect of the mixing the data may not have a big effect, but encoder definitely, which is more like a language independent the property, having a language independent property. So mixing the data means we had more data. So this is the reason that we even improve the performance. And as I mentioned, we just making it the one single neural network. So it's actually internally have a language identification. And we can also even perform whether a language recognition, the performance, whether the utterance is spoken by Chinese or English or Japanese and so on. And as you can see, this the performance is almost perfect. It can the perform very high accuracy language identification, and also single neural network, single system to realize 10 the speech recognition. I have several examples of the low resource language and so on, but I skip it. I also have a lot of how to say the code switching experiment as well, but here I just skip some of the result. And yeah, this is usually I kind of ask a question. The actually this work I kind of the submitted to this result to the one of the conference ASRU, and this was one of the easiest research for me. So of course, given we have a stably working attention-based encoder decoder, but given that this multilingual speech recognition was quite easy research for me. First, how many people were involved in this development? 10 language speech recognition. It sounds like we need a lot of kind of effort, but basically only one person, me. Of course, again, the other part of the developing the attention-based encoder decoder, Takaki or Suyon or other people contributed, but particularly this work, the 10 to build a 10 language, only one person. This is because, for example, to build a system, what we need is only for the data preparation. Only we kind of prepare the 10 language pair data and mix everything and then throw it a single neural network to train it. That's it. So actually my kind of a programming scripting work, it's just 1 or 2 days. And then of course at that time, it takes time to train the model since the GPU was not very fast at that time. So I needed to wait 10 days to finish the training. But basically that's it. And I basically don't need any kind of linguistic knowledge. I just kind of, converting everything to the Unicode so that it can be a kind of a programming friendly the situation. That's it. And again, with this, I can actually write the paper and I can get the best paper candidate. By the way, not the best paper, just, one of the kind of the, how to say, selected best paper candidate, but it's very kind of honorable, the outcome. And again, I just want to mention that this work, in terms of the man effort, one person, a 2-day effort. Of course, writing the paper and so on, it may take time, but a couple of days are fine to write the paper and get the best paper candidate. I believe some of them that want to, have a lot of research ideas and so on. Sometimes, some of the research, it takes very long time. But some of the research, if we find a interesting problem and having a good platform, we can write a paper with a quite small effort. This is one of the example. I was very lucky to, again, I was one of the early adopter of the attention-based encoder decoder. And people don't have such kind of systems at that time. So I can have a lot of idea, stable implementation. It's working with a small amount of training data as well. That's why I can make such kind of a research. Yeah, and so on. And I can also show one of the example of the audio, and this ref means the reference. It's actually mixing several languages artificially, and this is a speech recognition result, almost perfect. Let's listen to the audio. I believe it would work.
Segunda-feira.
Das gilt natürlich auch für bestehende Verträge.
同一人物による異なるメッセージを示しております。
Yeah, this is a simulation of the mixed language, and it's real code switching. Of course, same person to switching the other the languages, so it's more difficult. But anyway, one single neural network can solve this kind of a speech recognition task in the mixed language. Okay, now I think I have several the chat.
They're just comments.
Okay. So then I can I have 10 minutes more, right?
Yeah. So go ahead.
Yeah. It's actually just the beginning of 2 years, and now 2017, 18, 19, 2020. So I mostly skip many of the materials that I prepared. I'm so sorry about the wrong, how to say, the spending the time for the entire lecture. But I quickly kind of remark the rest of the research history of how I kind of do it. these previous studies, I actually have done most of the things in the company, Mitsubishi Electric Research Laboratory. Biksha was also, Biksha used to be there. We didn't have an overlap, but the Biksha was also working at that company. It's have a very good the culture of working on the fundamental research problem, and a lot of kind of fundamental research that we can tackle even in the company. So I really enjoyed my kind of research life at the MAR, Mitsubishi Electric Research Laboratory. But then I had an opportunity to move to the university academia, and I moved to Johns Hopkins. And what I was thinking is to share this knowledge, experience to the community. Again, 2017, I believe a lot of big companies started to play with this kind of attention-based encoder decoder or CTC, including CMU here. But it was not widely used for the small research institute or academia. So my kind of the interest is to share this kind of exciting research topic to the community by using the open source. And then I actually started to develop the project called ESPNet, end-to-end speech processing toolkit. And that is actually now it's getting quite popular. We have a totally more than 3,000 GitHub starts, and around 100 people are contributing. And actually, I am the original author of this the toolkit, but most of my kind of original code was replaced by the other people. But anyway, the major concept is again reproducible end-to-end speech processing studies for speech researchers. And we also focus on the simplicity, because if it is complicated, other people cannot follow. So we try to keep the simplicity. And also we try to make it smoothly the working parallelly with the Carnegie, another very famous speech recognition toolkit, so that we can easily compare, or we can easily port these ideas between Carnegie and the ESPNet. And we implemented hybrid CTC attention, and we actually are having a lot of effort of the initial development. And then it turns out that this architecture is not only the important for the speech recognition, but it can be applied to the TTS, speech translation, speech enhancement, and so on. We call it ASRX. Actually, that was a little bit my original intention as well. So the sequence to sequence is quite general. So once we have this kind of a the toolkit, we can actually use the same model, but changing the input to apply to the speech translation, TTS, ASR, speech enhancement, and so on. Thanks to the general the framework of the sequence to sequence. So now this project, again, I don't call it this project as a speech recognition project. This is a speech processing project, including all of the speech processing the applications. Actually, now we are supporting this kind of all entire the applications. And that is again that comes from the one unified view of the sequence to sequence problem. What is the sequence to sequence problem? We have an input of the sequence. We have the output of the sequence and the function that is written by single neural network. This kind of a general the mathematical framework is actually quite important when we also design the software, so that we actually making the ESPNet. Again, first our instance here was the speech was input and the text was the output. And this part is attention-based encoder-decoder. But since this general framework is powerful, we can actually support text input and the speech output, which correspond to the text to speech synthesis. If input is English speech and output is German text, this is the speech translation. And if input is noisy speech, and if output is clean speech, and then it becomes the speech enhancement, denoising problem. And what toolkit should do is to design the function part. And we prepare CTC attention and again joint CTC attention, RN translator transformer, and just changing the input and the output, we can support this kind of wide variety of the input and the output conversion problems. And note that this unified framework is not only, of course, in the ESPnet. There are a lot of famous toolkit also having this kind of a concept. So that probably the Fear-Seek Nemo by NVIDIA would be famous for you guys, and Ring of Google, and Espresso is another kind of implementation by the Johns Hopkins team. These toolkit basically originally intended for, let's say, for example, machine translation and so on, but now covers speech translation or speech recognition and so on. So again, this the mathematical kind of the unification is also having a great benefit for designing the software. And the ESPnet was designed like that. And again, around this, inside this one, we put a lot of know-how, basically based on the hybrid CTC attention. So that is a kind of the introduction of the open source the toolkit, and given that we also found the other possibility of the integration component of the speech processing by using this kind of framework. But unfortunately, I just have a couple of minutes, so I kind of skip this part. But I just want to mention that if we have one single neural network, we can combine ASR, TTS, machine translation, everything in a single neural network.
Shinji, we can go a little over, but I think showing them the speech enhancement one would be really interesting.
Yeah, this is only one slide, but that is the very kind of interesting the application. So this one of the application of the integration is the speech enhancement and the speech recognition. For example, speech enhancement is the including the deliberation, removing the echo noise. And the beamforming is to removing the noise and so on. These parts we actually have a separate module. Amazon Alexa, the Google Home, they are actually having a separate module for the deliberation and the beamforming and the speech recognition. But what single neural network can do is once written this part of the neural net, this part of the function as a neural network function. Let's say this the speech enhancement is actually written by the basic linear operation. So we can write it as a PyTorch function. And then this part is also single neural network. So written as a PyTorch function. And combine it and only train the input of the noisy signal and the text component, but by using the back propagation. By using that, we can train both speech recognition, speech enhancement by using a single neural network. That integration is one of the great example of the neural net end-to-end neural processing approach. This part I have a more kind of slide if we want to know more about it. I'm happy to elaborate in some the other occasions, since I will join CMU to January. So we'll have more opportunities to have more interactions. And yeah, separation can also be performed, same methodology, having a different separation, speech separation component, and having a different the speech acquisition component, one single neural network, back propagation. This kind of the integration and the single back propagation, that kind of methodology is, we turned out that it is very powerful approaches. And another very nice example is the speech acquisition and the TTS. It is also another kind of very different application. But if we combine speech acquisition and the speech synthesis, TTS, we can convert speech, text, speech. And let's say that we only have an audio on data. We don't have a corresponding text data. We can actually train this speech acquisition and the TTS jointly by only using audio data. We can also do the vice versa. Only text data, TTS, SR, and then we can jointly train speech recognition and speech synthesis by using a single neural network. So yeah, that is a kind of the great benefit of the integration. And having a lot of improvement, I just kind of skip this kind of approach. But the overview of improvement is that as soon as we got some new techniques that are developed in the computer vision or machine translation, since now all the kind of component is written as a single neural network, we can easily incorporate this kind of the exciting architecture, and we get a very good performance. So that's why improvement is also kind of very impressive from the 2018 time frame to the now. So that is the entire research history of what I have developed this end-to-end speech recognition. Sorry that it takes a little bit longer time than I expected. Yeah.
Perfect.
Any
Thank you.
questions?
Yeah,
Sorry,
so,
maybe we don't have time. So
no, but
I can...
so students, do you have any questions? We still have most of the students on. I'm not really seeing any questions on chat. I'm sure there are questions. Yeah. Apparently not. So that's okay. We get questions on Piazza.
Yep.
We'll handle
I
it.
have a question.
Yes.
Question?
Go ahead, Mitch.
Professor Watanabe, thank you for your talk. I was wondering, I saw on one of your slides the training time is in days and sometimes weeks. So how do you, in the intermediate learning steps, when you're trying to make sure that your model is actually going the right direction, because retraining is very expensive, how do you iterate through those hyperparameters? You said that it doesn't really matter, but I'm sure that there's some magic that happens.
Great question. This is one thing we have to care in this kind of deep learning. And my suggestion is, again, checking the learning curve. Checking a learning curve often. If today not, but I usually, for example, my monitor, one of my monitor was occupied by a lot of the tensor board. And I am kind of always, writing the email or, making a slide or sometimes programming, but another monitor always kind of a tensor board is showing the progress. And I'm actually always monitoring how learning curve is behaving. And yeah, if there are some wrong things happen, we can easily detect what wrong in the very beginning of the learning curve. So I strongly recommend you to very carefully checking the learning curve. And yeah, sometimes it's getting normal and sometimes it's not. But in general, the beautiful learning curve is that, let me, let me try to share the learning curve slide. Yeah, actually, I got a special skill now to how to say find a good learning behavior. But yeah, this is a kind of a typical learning curve. I would say it's a very good learning curve. The validation and the training curves are looking kind of a similar the behaviors. And then once the training goes, validation part is getting converged, but still training part is little bit kind of improved. It is more like a little bit very small overtraining, but it is acceptable. But this curve is very different. And then there is some problem, which can be detected by when we checking the later part of the epochs. But your question is, early part, how do you detect? Yeah, you can still check this kind of learning curve. Usually both training and the validation are going a similar curve in the beginning of the epoch. So I recommend you to check this part. And also this behavior may change if you use, for example, dropout and so on. If using a dropout, training problem becomes actually very hard. So that training performance is actually very bad compared with the validation. So this learning curve may also depend on some other regularization techniques. So I don't fully, mention, some perfect answer of the situation. But in general, if you always looking at the learning curve, and then you can actually detect what happened in the early stage of the training.
Okay.
I also have a question.
Yeah.
Yeah, because Professor, I have been studying Japanese for a year, so I'm very curious about how can you differentiate between katakana and Roman alphabet? Because I know a lot of katakana are used to represent English words. So how do you differentiate them? Because I think they will have very similar symbol.
So frankly, this part, we didn't do any model. We just kind of rely on the corpus. So if some of the corpus, for example, same the pronunciation, but it's written in the katakana, then the majorly in that corpus is the just kind of producing the katakana script. And if it is the Roman alphabet often, and then it's the neural network predict the Roman alphabet corresponding the same the pronunciation. So this is the one of the kind of how to say the good part of or bad part of the neural network. If we have such kind of a large scale corpora network can actually predict such kind of same the same pronunciation or even same word, but a different script. But depending on the context, they can actually produce two results. But we actually not easily find what's happened inside. Whether this neural network can well capture the correct pronunciation and select either of them. Also, we cannot force them to only kind of output the one of the script easily. So because we don't have an explicit representation of the single neural network. So yeah, the answer is that can be just simply handled by the black box neural network with the corpus.
Okay, thank you so much.
Yeah, this is the sounds nice, but it's actually drawback, right? Yeah.
Anything else? All right, folks, I'll stop this right here. Thanks a lot, Shinji. This was an amazing talk, as always.
Thank you so much.
Yeah, and how does one even stop the recording? I'm sure. Yeah, stop.
Okay, then.